All right, so welcome back. We are kind of wrapping up our last unit here about reaction rates and how reactions happen sort of at the atomic level and things that affect how fast those reactions go. So what we're going to talk about here today is something called the collision model, which is a way of understanding how reactions occur at the molecular or the atomic level, and then some of the things that can directly influence how fast a reaction occurs based on that idea of the collision model. So by the time we're done with this, you'll have an understanding of what the collision model is, and then the there's four categories of things that can affect how quickly a reaction proceeds. So here we go. Number one, in terms of talking about reaction rates, there's a few things to kind of understand. Is that a lot of times in a Chem 1 class, we do a lot of very simple spontaneous reactions. You know, you put two things together and poof, the reaction happens really quickly. In the broad range of everything that is chemistry, in fact, reactions can occur at a whole variety of different rates. Some of them are incredibly slow, and then some of them are pretty much immediate, like the ones that you're used to. And then some of the ones are so immediate as to be kind of scary fast. And then there's everywhere in between. So when we talk about reaction rates, we have to kind of have that understanding somehow that there are indeed different speeds of reaction. So I've got a couple examples on here, like, watching something rust, an incredibly slow reaction. It takes, years for that reaction to progress, even though it's spontaneous and it happens all by itself, versus the dude hold my beer at the bottom running around with the flaming gas can, everywhere in between. They showed the one with the contact lens solution on the right. If you have contacts, you may have recognized that one. It's a hydrogen peroxide reaction, which just kind of fizzes a little bit. But everywhere in between, you can have hydrogen peroxide, like the stuff in the contact lens solution case, that's so strong and reacts so fast that it can basically explode, which is kind of scary. So anyway, there's every range of different type of reaction rate, from incredibly slow to, yeah, dude, hold my beer, and then, everywhere in between. So what are the things that control how fast these reactions occur? Why are some of them so slow and why are some of them so fast? So first things first, let's talk about how reactions happen. In terms of having something actually come together to react at the atomic level, it sounds kind of funny, there's a few basic things that you need to have happen all the time. Like number one, the reactants actually have to come into contact with one another. So that means, an atom of A and an atom of B literally have to collide. That's why they call this the collision theory. The next thing that happens is if you're dealing with compounds that are reacting together, you have to break the original bonds that are present, and then you have to sort of rearrange the atoms, let them find their new partners, and then form new bonds. So it's actually kind of complex in terms of energy at that atomic level. So this idea, the fact that two atoms or two molecules have to come together, collide, rearrange, and then separate again is what's called the collision theory. And there's a few things about this collision theory that really can help us understand why some reactions are fast and some reactions are slow, or how to make them go faster or slower if we want to. So number one, it's important to keep in mind that when we're talking about chemical reactions, every time two atoms come into contact with one another, they don't necessarily have to react. And so this little diagram on the left, we've got a couple of things. Number one, you can have two things coming together too slowly, so they just bounce off one another. Or the second case on that picture there, where they can come together at kind of the funky wrong order, where they just don't quite hit and rearrange correctly. Only certain things can combine to actually have a reaction to go. So in terms of these things, we have to affect these factors in order to make the reaction happen more quickly. So number one, you could have atoms coming together to collide more often. The more often they collide, the better the chance is that they'll come together in the right orientation with the right energy to make something happen. Number two, we can increase the amount of energy in these collisions so that when the atoms come together, they're more likely to be able to break and rearrange and create new bonds. And then the next one that comes together is we can sort of do things to help ensure that they come together in the right orientation to make them meet their new partners as efficiently as possible. So all of these things, in terms of modifying these particular parts of the collision theory, it ends up being four factors that we can do to affect all of these different things. So we're trying to make them collide more often, we're trying to make them collide with more energy, which is actually the most important part, and then we need to make sure that they can collide in the correct orientation, the correct arrangement. So here's the four factors, and yeah, I will ask you what the four factors are. So here's the four factors. Number one is concentration. My little picture on the left there. Imagine the number of collisions that could happen between all of those cars. Imagine that each one of those cars is a chemical molecule, right? Well, the lane on the left that has all of those cars packed in there, the amount of collisions that could happen in a second could be quite a bit higher than that lane that's on the right where there is no traffic jam. We have a much lower concentration on the right, so the chances of a collision there are quite a bit less. So with these things, anytime that you have more molecules per square inch, that's a higher degree of concentration, and that that can allow for more collisions to happen. So with these things, we can talk about solutions. The amount of reactant particles per liter or whatever is called molarity. If you're talking about something that's a solid, the way we can sort of increase the concentration of a solid is by powdering it, by increasing that surface area. Because remember, if you're talking about a solid that's reacting, only the outside surface can actually be directly involved in a reaction. So if we crush it, we get lots more outside surfaces that can get involved in there. And then if we're talking about gases, the way you can increase the concentration of a gas is by increasing the pressure. You're smushing more gas molecules into a smaller container. And again, that's an increase in pressure for a gas. Keep in mind that having just more collisions isn't really necessarily enough to make sure that more reactions occur. It just gives you more chances of it happening. But the most important thing is that you have to have the right amount of energy. So having lots and lots and lots of very low energy collisions isn't going to do anything for you. You need to have high energy collisions, because with the low energy collisions, they're just going to bounce off of one another and nothing really new is going to be formed. So that's the reason number one. This idea of concentration certainly helps, but it isn't the only thing that will help a reaction happen faster. And this gets us to number two. Number two is to increase the temperature of a system. And you guys know this from your everyday, that the more temperature that you have in a reaction, the warmer it is. This is where, well, duh, the more likely it is to react. That's why we cook our foods at temperature, right? That's why we use refrigerators to slow down decomposition reactions so our food stays fresher longer. But the question now is why? In terms of the collision theory, why is it that temperature has this effect? So I've got my two temperature pictures here, right? My picture on the left there of these cars kind of going slow, sort of my low energy picture. My picture over here on the right, yeah, which is not real, but it's cool anyway, is a picture of these cars going at much higher speed. That represents our higher temperature. So in terms of these things, temperature is a measure of molecular motion, molecular energy. The higher the temperature, the faster the atoms or molecules are moving within that particular substance. And we're talking now, you know, at the atomic level, how quickly are they moving? Not talking about throwing a solution through the air. I'm talking about the atoms within that particular solution. So the faster the atoms are moving, the higher energy collisions they can have, just like with our cars here. Those cars on the bottom right going faster can have a higher energy collision than any little fender bender that might be happening between those cars that are stuck up in the left in the traffic jam. You know, if they touch, they're just going to bounce off one another, not going to really rearrange parts like the NASCAR cars are. And what's important about this is that, again, when we're talking about these collisions, you have to have enough energy to break and rearrange bonds. And that's what the temperature provides, is enough energy for that to happen. And then the last thing that happens too is that, and this isn't the most important part, but as things are moving around faster, you can also get more collisions. It sort of has a way of almost increasing the concentration without really changing the number of molecules. And again, think about if you've got particles moving slowly, say 5 particles, and they're just kind of moving around real slow, they might hit one another, but they're not going to hit very often. If you have 5 particles moving really fast and you do the same, you know, let them bounce around really quick, you're going to get more collisions in a certain amount of time. But the most important part with temperature is that temperature provides the energy for those collisions to achieve that bond reformation that they need, bond breaking and bond reforming. So number 2, temperature. Number 3, something called catalysts and enzymes. Catalysts and enzymes are something that you would add to a reaction. It's not something that's within the reaction itself. It's something that you kind of place in there to make this reaction happen both more quickly and more easily. So again, it's not naturally a reactant or a product. It's something else that you're adding to the system to sort of facilitate the reaction that's going on. The only difference between something that we call an enzyme and a catalyst, and if you had biology last year, you probably remember the term enzymes. Enzymes are simply catalysts that happen in organic creatures, you know, biological catalysts. So they mean the same thing. So what you understand about enzymes is fine, and catalyst is just a broader term. Enzymes are a type of catalyst, if you want to think of it that way. So with these, keep in mind that enzymes and catalysts don't change reactions. They don't make new reactions occur. They just make the reactions happen more easily. And the way that they do this is by allowing the molecules to come together, A, more easily, but then B, in the correct orientation. They're actually kind of snuggled up right next to one another in the right way to help break bonds and then reform bonds that are correct. The other nice thing about catalysts that makes them a little bit different than some of the other things we're talking about, that catalysts are completely reusable. A catalyst can help 2 molecules come together over and over and over again, and they reset every single time they get used. So they are, once you put a catalyst in there, man, it just keeps going until all of the reactants are used up. So that's something that's really useful about catalysts, is that they're sort of infinitely reusable. The way that we describe how catalysts work is something that they call the lock and key model. And that kind of means that, well, if you have one lock, it goes with one key that goes along with it. And basically what that means here is that these things have to have the right shape. Just like a key has to have the right shape to fit in a lock, well, the enzyme itself has to have exactly this right shape to bring together the exact right molecules together in the right orientation or in the right alignment to it. So the spot where the enzyme can collect the reactant molecules is called the active site, and it's the part that has the funky shape that allows things to come together. With this, what it does is it either puts the two molecules close together so that they can bond, or it puts a more complex molecule in there so it can break them apart. But it just puts it in there in just the right way to allow for that bond breaking or bond formation to happen very easily. We're increasing the number of correct alignment collisions that are happening here. And then what's nice about this is after it's done, just like a lock and a key, you take the key back out. You can use the key over and over and over again. The same thing is true with a catalyst, is that once it's released the product, then it's ready to grab more reactants and then to recatalyze that reaction over and over again. In the real world, oftentimes many thousands of times per second. It's ridiculous how fast it goes. And then the last thing I guess to talk about with catalysts is to keep in mind, just like keys are specific. You can't put a key in any lock. It has to be the right key. And the same thing is true for catalyst. A catalyst will only catalyze one particular reaction. Any different reaction would have to have a different enzyme for it with a different shaped active site, just like you'd have a different key for every lock. Even like some keys kind of look similar from a distance, if you may be able to even get it to fit in there in the lock, right? But then you turn it and nothing happens. So the same thing is kind of true with catalysts, is that we've got thousands of different catalysts for thousands of different reactions, and each one of them will only catalyze one reaction. It'll do it over and over again, but it'll only do one. And then again, I mentioned this earlier, is that enzymes and catalysts are basically the same thing. We just talk about catalysts in biology as enzymes. So there you go. The way that these things work, not only by bringing things together and helping things, kind of either snuggle up or whatever, is they also do something called lowering activation energy. Now, we've talked about activation energy in the earlier lesson in this unit, about that bump up of energy that you need to get a reaction started, that initial investment to break some bonds before you can form new bonds. And what enzymes do is that they make reactions more easy by simply lowering that activation energy. You don't need quite as big a bump. So in terms of what they're doing, number one, they're bringing those bonds, the reactants together in the correct alignment, which makes bond breaking more easy, but it also makes bond formation easier as well. So both of these together are very useful to it. But again, it's having to do with lowering the activation energy to it. So if you take a look at this graph that's over here, you can see this lower dashed line right here, this little one, is like how much energy you would need to put into this reaction with the catalyst, as opposed to the big bump at the top is how much energy it would take without that catalyst. So the reaction will happen without the catalyst. It just needs more energy to do that. So if you can make it easier for that reaction to happen, it's going to happen usually at a lower temperature and more quickly, simply because it's easier. Keep in mind that this is an important part about what catalysts do, is that they don't change the overall amount of energy that's created by this reaction. And so what we want to take a look at in this graph here is the distance between the reactants and the products line. It's this green arrow that's facing down. That's the amount of energy that's released by that reaction. That does not change. It doesn't change anything about the reactants or the products. What it does change, though, is the amount of energy that you have to put into it. So it changes the amount of investment that you need. So in that sense, I guess there's a little bit of a net gain because you don't have to put as much in. You get the same amount out. So, it's still kind of a win-win in terms of that. But that overall energy is not changed at all by the catalyst. It just reduces the activation energy to it. Last thing, and this is kind of the weird one in terms of number 4. So we've had 1, 2, 3, and 4. Number 1 is the idea of concentration with solids, liquids, and gases. Number 2 is the idea of temperature. Number 3 is the idea of adding an enzyme or a catalyst. Number 4 is terrible. I hate this idea. But number 4 is a sort of grab bag idea called the nature of reactants. In other words, the chemicals themselves have different things to them, different atomic level things that change how quickly they'll react. So here I've got 4 crowd pictures. I couldn't find good pictures of cars that would work for this, but I found 4 crowd pictures. You can imagine that the amount of collisions between people would be different in each of these situations. Now, why is that? Well, if you think about the people in this picture up in the top top left here. Here they're sitting all nice in a range, or they're sitting in rows, they're watching some sort of event or a lecture, something like that. Pretty low energy to begin with. They're pretty satisfied with where they are. Then you get down to the beach picture, and yeah, you get people moving around, they're happy, okay, got some more reactions that are going on there, versus our crowd surfing friend down here, which is definitely going to be a little different nature of reactions. You're going to get a lot more collisions, a lot of more crazy things going on, because it's just a wilder crowd. And then if you talk about that bottom right one, where you've got like a riot going on, this is like some seriously reactive kind of things going on, right? You've got some serious aggression going on, different people involved in different circumstances. Well, you can have different types of atoms that are involved in different circumstances one another as well. And sometimes they react more easily and sometimes they don't. So in terms of kind of generalizing this back to the actual chemistry part, ionic compounds tend to, not always, but tend to react more quickly because they have that positive negative attraction to one another, that sort of magnetic attraction. Those bonds can be broken and they snap together really, really quickly. So those sorts of reactions can happen fast. And many of the reactions that we've done in class that look instantaneous, like our precipitation reactions, are ionic reactions. Again, because those ions can separate, reform together, and it's very, very quick. On the other hand, covalent compounds, when molecules are involved, that tends to be quite a bit slower. Molecules are stable. They've got a sharing arrangement. They're much more reluctant to break the bonds that were there and then form new bonds. They tend to be more complex that way. So reactions between covalent compounds, just in general, tend to be sort of slower than reactions between ionic compounds. We also have things like we've talked about activity series or reactivity series. Certain types of metals, for example, act with hydrochloric acid more quickly than others. And again, this is more typical down to, or more likely down to the atomic level. How are the electrons arranged? How big is the nucleus? How many protons are present? How many valence electrons does it need to gain or lose? So at that level, you can have differences between the reactants themselves, even things that look similar on the surface. And that, again, can make it easier or harder for reactions to occur. And then finally, you can have the compounds themselves. If you have two single atoms that have to come together, that's pretty quick and easy. If you have some compound that's got 7 different atoms that all have to come together and rearrange, it's just a lot more challenging to get that to happen, and that's going to be a slower process in general. So anyway, this idea number 4, this nature of reactants, it's kind of the junk drawer idea that there's all this other stuff that's going on down at the atomic level that can make some reactions happen quickly, and then make some reactions just happen slowly, just by nature of what the things are that's involved. So there you go. To review kind of what we were talking about today, we started by talking about just that idea that there are reaction rates, that they're different, that there's some that are super fast, and there's some that are just ridiculously slow. We tend to do faster ones, but not dangerously fast in the Chem 1 class, just so we can actually see them and not watch, something rust. Woohoo, right? And then number 2, we talked about what the requirements for a reaction were, that in order to have a reaction happening at the atomic level, that you have to have atoms or molecules come into contact. They have to collide. The bonds that were there have to break and then rearrange. And then we started to talk about how those things are that we could affect that rate. So number 1, concentration, and that concentration can increase the number of collisions per second because we simply have more atoms or reactants present in a container. We talked about molarity, surface area, and pressure, the way that concentration sort of gets affected between either solutions, solids by powdering them at the surface area, or with gases and pressure. The second thing that happens is temperature. Temperature increases the amount of energy that's present for that bond rearrangement. And remember, no matter how many collisions that you have, if they don't have enough energy to actually rearrange, then they're kind of worthless collisions. So temperature is actually really important in terms of increasing reaction rates. We talked about how catalysts and enzymes work. That's something that you add to a reaction to make it happen, that they're very specific, like a lock and key, that they have a particular kind of a shape that makes them work. And then we also talked about the fact that the way that catalysts and enzymes work is by lowering activation energy. They make the collisions easier, but they also reduce the amount of energy needed to do the rearrangement. And then finally, I just talked about the nature of reactants. It's, again, the one that's sort of annoying, where everything breaks down. Oh, can you hear Sierra coughing? She's got a virus. Poor kid. She says sorry. Anyway, the nature of reactants is that last terrible grab bag one, where there's all different kinds of things about the structures of the bonds that are already there, or the types of atoms that were there, or the size of the atoms that can make things happen quicker or slower. Like ionic compounds tend to react more quickly than covalent compounds do, and that things about, say, the structure of the electrons or the structure of the atom can have some effects on that. So there you go. How to know what the collision theory is, that we need to have collisions for reactions, and then how we can kind of use our understanding of the collision theory to figure out how reactions can go more quickly. So in the next couple of lessons, we're going to take a look at reaction rates in forward and reverse reactions and how those compare with one another. So there you go, and I will see you in class at some point in time, right? Have a good one.